Well, thanks very much, Kumar. Thanks for the invitation. It's always well, I was going to say it's certainly a pleasure. It's a strange thing, of course, to give talks in this format, but we'll see how it goes. So again, please, ask me some questions if you need some. So this is joint work in progress, hasn't been submitted yet. So things are, the final statements might be a little bit stronger. They won't be weaker. But joint work with Adela Gherga and Samir Siksek, both at Warwick, and Vandita Patel, now at the University of Manchester. So I'm going to talk about values of the Ramanujan tau function. It seemed an appropriate one for a seminar where we're hosted by Kumar. As most of you, I guess, would well know, that the Ramanujan tau function, defined as Ramanujan does, is the coefficients of this particular sort of weight 12 modular form. So explicitly, you see down here, we've got, it's a cusp form. So we've got the coefficient of 1 is 1. And then we see the coefficients of the primes, 2, 3, 5, et cetera, minus 24, 252, 48, 30, et cetera. So a beautiful looking object, studied classically for many reasons. And so there are lots of properties we know about it and a number that we're not so sure of yet. But of course, conjecture by Ramanujan, proved by Mordell that it's actually multiplicative, and that's going to be useful for us, certainly as we go along. Multiplicative function. So if you have relatively prime integers n1 and n2, then tau of the product is the product of the values of tau on those integers. So we can understand its parity very, very easily by writing tau. So it's congruent to this sort of second quantity here, this product. We go from the sum to the product, and then we can expand that out. Oh, maybe there's a bit I can't see very well here, but let me see. I'll change that down. We expand that out, and then if we apply Jacoby's triple product formula, so if we take that formula as you might know it, we'd replace the q. There's a q and a z in that formula. It's not the same q here. Replace that by q to the fourth, and replace the z by q squared, and do a little manipulation. However you get there, you can find that in fact we have a congruence mod 2. Lots of things drop away between this series with tau as coefficients and this series with zeros and ones as a coefficient. And that tells us in particular that tau is almost always even. So it's odd only when the argument you put in is an odd square. And it also tells you in particular that tau of p, as we saw before, tau of 2 is sort of 24, that tau of p is actually even for every prime p. Okay. So I want to talk about sort of arithmetic properties of the tau function. And one thing we have sort of beautifully, and this is again part of much more general theory by Deligne on the size of Fourier coefficients of modular forms. But so originally conjectured by Ramanujan, we have this very nice upper bound upon the size of tau of p in absolute value, bounded by something of order p to the 11 over 2. And of course, you can then use the multiplicativity and the recursion, I'll show you later, to actually get then a bound on tau of n, which is roughly of the same order, n at 11 over 2, but then you get a divisor function that comes in, which is of smaller order, but still can go to infinity. So we have that as an upper bound. And if we go in the other direction, again, as part of a more general series of conjectures for weight, sort of k modular forms, if we take k to be 12, we would get this. And this is a conjecture of Atkin and Lehner, and sort of a very great strengthening of like a Lamer's conjecture. So Lamer's conjecture that tau of n never vanishes is equivalent to showing that tau of p never vanishes. And sort of going further from vanishing, we could say, well, the conjecture is really that it grows polynomially in p, like basically p to the 4.5. So in particular, if I give you some fixed integer like 12, there should be finitely many primes p for which tau of p is equal to 12, conjecturally 0. But the tricky thing here is we don't know any statement of this form, sadly. We really can't prove anything much here for tau of p. I mean, of course, if we know tau of p is even, so if we take a to be odd, then there's no solutions. But apart from some sort of local obstruction like that, there's not much we can say here. So if in general, we can't say much, but if we actually do make the right-hand side odd, so that in particular, the argument that tau takes can't be a prime, it would have to be an odd square, then there's a beautiful paper of Murty and Shorey going back quite a long time for some of us, that in fact, tau of n will represent A at most finitely many times if A is odd. And stronger than that, they prove that the absolute value of tau of n, if tau of n is odd, grows like a power, a positive power, that's sort of important, of log n. And so in particular, this tau of n goes to infinity as n runs through odd squares. So this might not be a couple of comments to this. This is, the truth is something stronger than this. This is, but this is what one can prove in general. One can prove much stronger statements if you assume the ABC conjecture. If you assume, if you're looking for an average statement or for infinitely many n kind of statement, the constant here C is extremely small and positive. You can work it out, but it's coming from, again, this one's coming from linear forms in complex logarithms, so it's going to be quite small. So people have sort of followed up on that recently. They've very recently, they've basically said, well, okay, can we actually use this? So the bounds a priori you get from linear forms and logarithms are very, very big. They're big enough that it doesn't really give you an obvious way to approach this, but as we've seen in many other cases, such bounds, you combine it with, say, lattice spaces reduction or other techniques from computational Diophantine approximation, you can often reduce them to something kind of plausible, and then finish off the problem. So recently, there's a number of papers solving such equations explicitly, well, actually showing there are no solutions for small odd values of A. So the first I've seen of this, and other people have noticed this, is mentioned, at least the argument is there. It's not, all the details aren't filled in, but it's by Algebraic and Rosier, showed that there are no solutions for tau being plus or minus 1. And then for tau odd primes, up to 100 or so, there's a collection of papers by Balakrishnan and Craig Ono and other co-authors and other people from, I guess this is an REU, so it's an undergrad summer research project out of, I guess, Virginia, so based around Ken Ono, for A odd primes, and then sort of filling in some composite values as well. And the approach will have some similarities to what I talk about, so I'll mention more about that in a bit. So what I want to really talk about is sort of if you like, a non-archimidean analog of the result of Murty and Shorey. And we show that, in fact, that we can basically show that either Lamer's conjecture is false, or the greatest prime divisor. So not just tau of n grows, but the greatest prime divisor of tau of n, as if tau of n is odd, that should go to infinity. And notice, well, I'll say a little bit more about that right-hand side. So it's a function that goes to infinity in n. The n greater than or equal to 25 is just to make sure that it's well-defined. Okay, and so I just want to mention a little bit more what we actually prove. So the techniques here, the techniques we're gonna use won't work at all if there exists a prime that just divides my integer n once. Because then with multiplicativity, you need to understand tau of p, and we just don't. But we do understand tau of a power of p. So we call a powerful number or squareful or twoful, it's just an integer with a property that if p divides it, p squared does. So equivalently, you can write that integer as a square times a cube. Okay. So what we actually prove is a result through powerful numbers. So we again, you could state it if you like, that if either Lamer's conjecture is false, or we get a lower bound, again, if this shape, an absolute constant, absolute positive constant, and then it's log, log, log over log, 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 the traditional sound of somebody drowning that comes up in analytic number theory. And so it's a truly dreadful bound on the right-hand side. Notice if you put in something like n is e to the 10 to the 1,000, this number on the right-hand side, apart from the kappa, is something like 3. It's not a very practical bound. So you're not going to actually use this in any real cases. It's more of a theoretical, what can one say kind of bound. And the truth is presumably much better than that. Probably something like log log. In that neighborhood, I would guess. I don't know if one would really do much better than that. even under pretty heavy assumptions. Okay, so let me just mention that the Lamer conjecture part, and it's not just because the techniques we're using fail. They do fail, but it's that the statement that the greatest prime divisor of tau of n goes to infinity is just not true if Lamer's conjecture is false. So if Lamer's conjecture is false, then tau of p to the k is just a power of p. And so the greatest prime divisor of tau of p to the k is bounded, independent of k. And so through this subsequence, this result fails. So if we want to get any result that says that the greatest prime divisor of tau of n goes to infinity, Lamer's conjecture has to be true. Okay. So, and again, Lamer's conjecture, we don't know really much about it at all. We do know that if there's a counterexample, it's quite big. This is, as far as I know, the state of the art is a result of Derricks, Van Hoij, and Zeng. And P has to be bigger than, I can't even count that. That's, more than 10 to the 20. It's big. Okay. So it depends. If you're an engineer, then Lamer's conjecture is clearly true. If you're a mathematician, well, it's probably pretty much true as well. Okay. And it fits into some broader context of conjectures about the growth of Fourier coefficients of higher weight modular forms. Okay. So just to say what we actually prove, so we again use multiplicativity of the tau function, and we sort of go and look at tau of p to the m. Here m is at least 2. We need that, and we show that for small m, then we get a growth of the greatest prime divisor of order log log, and for larger m, we almost get that. We get log log and then some other smaller factor. So log log to the power 1 plus the low of 1 as lower bounds. And this is all we need to prove our result. Should mention that there are other results in the literature. There's a result of Luca and Sparlinski, who prove a lower bound on the max of the greatest prime divisor of tau of p squared and tau of p cubed. They show that at least one of those is a little bit bigger than log log. So here we're not getting bigger than log log. We're getting either equal to or of that order or a tiny bit smaller. They get log log, and then it's something like log 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 over log 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 log. But that's for the bigger of 2, and they can't tell which. Okay. So a note that the results here don't imply that, nor are they implied by it. So they're just independent. Okay. And so anytime somebody states an appalling result like that really has no explicit value because the numbers involved would be so colossal, it's perhaps interesting to know whether you can make it explicit. And so I want to demonstrate, and the techniques are actually rather different for doing this, that we can actually prove something along these lines. So what we can basically do is classify all again, our techniques only work when we're taking n powerful, but we're going to classify all the tau of n that have prime divisors smaller than 13. And I'll say a little bit as we go about why 13, but essentially, if we stopped a little earlier and we just allowed 2, 3, 5, 7, the result's very easy. If we allow 11, it becomes hard and requires a lot of work. If we allowed 13, which we haven't done here, probably we can do it. It just depends on how enthusiastic we feel. If we allow 13 and 17, then probably we almost certainly can't do it without some new ideas. It would involve some enormous computations of spaces of modular forms that will be far beyond current technology. Okay, so if we want to sort of cut that down, then explicit result, if we want to make this look a little bit more like the original result we saw of Murty and Shorey, which said that if tau of n is odd, then p of tau of n grows reasonably quickly, or tau of n grows reasonably quickly. Then here we can actually essentially solve the equation tau of n is plus or minus a power of 3, 5, 7, 11, that sort of thing, and show that there are no solutions at all to that. So this takes care of quite a few of the sort of special cases. The earlier work of Balakrishnan and Ono and co-authors, this machinery can handle those cases, but we're interested a little bit more in the sort of these non-archimidean versions. Okay, so just to talk a little bit, another thing we can say a little bit about prime values. So it's one of these things that you get a lot of these. You have to work quite hard to find prime values of the Ramanujan tau function. But having said that, it's conjectured. I mean, I think the at least one claim I've read said that Sayre conjectured this somewhat explicitly, that this behaves like a lot of other things, like Mersenne primes or things like this, that is sort of a log going on here. That this thing should actually occur infinitely often. So tau of n and absolute value should be prime infinitely often, but it's a log thing. And so it's growing slowly enough, you might not find them very often. But anyway, here's the smallest prime value. The conjecture made quite explicitly is there's infinitely many of them. And there's a fair number have been found, mostly by Legeris and Rosier again. In our case, we're looking at not at the lower end. This presumably is the smallest prime that shows up, this tau of 251 squared. But that would be rather hard to prove. What we can prove is that there are no powers of any prime under 100 that show up, any odd prime under 100. And so here, whereas in the other case where we had a bound, we had all the primes up to say 11, and we could go to 13, but probably not to 17. Here we could go quite a lot further if anybody really cared. That's not clear that anybody does, but we could go rather further. So we could certainly push this to 1,000, for example. So that's just a matter of working a bit harder. Okay. So let me just give a sort of a little brief sort of executive sort of overview summary of how we approach these. And there's sort of two different sort of types of results. One is the one with many logs, and that is going to proceed essentially by sort of fairly straightforward arguments about recursion sequences combined with results. We have to use both Archimedean and non-Archimedean logarithms, so linear forms. So transcendental number theory, and that's, again, this was pioneered for this kind of problem by Murty and Shorey. And the second, the explicit results, we're not going to go that way. Well, that's not quite true. We are in part, but we're mostly not going to go that way. The hard lifting, the heavy lifting there is going to be done using essentially results from modularity. So we're going to actually construct Frey-Elguar's curves and make them do the work for us. Okay. And that, as far as I know, hasn't been really used in this context before. So other comments, of course, now, as I'll show you in a little bit, the thing that makes this all tick is this particular sort of recursion formula. And that's something that's much more general. So Deligne proved this much more generally for modular forms. And so this is something that's not a new observation. So this is really the best place to look for this is a paper of Ram and Kumar on extending these ideas to more generally coefficients of higher weight at least 4 cuspidal newforms with some particular sort of arithmetic constraint at 2. So you actually want the tau, the coefficient of p should really be even for all large enough primes. And so this particular case we're looking at is this level 1 weight 12 case where the coefficients are a Ramanujan tau function. We're just going to restrict to that for the arguments. But at any stage, you can sort of try to unravel it and say, if I'm seeing something that's coming from 12, I could replace that by k and see what the different result would be. But the machinery will essentially work. For smaller weight, like weight 4 or 6, some of the machinery I'm going to mention with coming from Frey curves is more complicated there, or potentially could fail. But in those cases, other techniques, transcendental techniques, work much better, or perhaps Chabati style techniques for finding rational points on higher genus curves. So I'm going to sort of segue into where this is, where we can sort of get our hands on this, and sort of the fundamental idea lying underneath this is a very elementary one. So we are going to look at binary recursion sequences. So a Luca pair is a pair of algebraic numbers such that their sum and their product are non-zero coprime integers. And to avoid degeneracy, we want the quotient not to be a root of unity. And so we associate to that a particular characteristic polynomial. So this is, again, just a degree 2, it's binary. And this thing will have a non-zero discriminant. And for a given pair of these un, which is sort of the the quotients of alpha to the n minus beta to the n over alpha minus beta, those alpha and beta are the roots of this polynomial, if you like, then these un give us a sequence of integers. And it turns out they're if we make these assumptions, they're relatively prime and they have lots of other nice properties. So in our case, we're gonna get this from looking at tau of p to the m, and that is generically going to be a Lucas sequence. So we're gonna have to look carefully at that because sometimes it isn't. So we have to at least classify that. And where this is interesting, it's this last equality down here. So you might think of this sort of a canonical thing. You might think of these as sort of, okay, how about the Fibonacci numbers? So that's a very simple one here. Alpha is going to be the golden ratio, 1 plus root 5 over 2. And that would make beta its conjugate. And in that case, beta has absolute value less than 1. And so what that means is that if you let n go to infinity, these u sub n's are basically just a power of alpha, because the beta and the n's going to 0. Okay, so it's kind of like a power of alpha. And so this is how you get this connection to transcendental number theory, because basically it's saying, hey, this recursion, this thing is a power of an algebraic number. And the idea is that if I give you two powers of algebraic numbers, for example, they shouldn't be close together. So machinery from linear forms and logs can give you explicit statements along those lines. So the two useful things, I mean, again, we're going to sort of convert our problem of understanding the greatest prime divisor of values of tau to understand the greatest prime divisor of elements in some one of these Lucas sequences. So the most important thing we're going to use, it's a relatively recent, beautiful theorem of Bilot, Enroux, and Voutier, is that if I give you a Lucas sequence, then from every term, from the seventh term on, if you like, every single element has what's called a primitive divisor. And a primitive divisor is just, it's kind of a new prime divisor that didn't divide anything earlier. So it didn't divide the discriminant of the sequence, and it didn't divide any of the earlier terms. And where that's really useful for Diophantine problems is if you say, hey, I want to find all of the things in this sequence that have no prime divisors bigger than, say, 11. Then if I look at this, it says, hey, everything's got a new sequence. So if I find ones early on that have my 2s and 3s and 5s and 7s and 11s, then go past in the sequence, there must be a prime that isn't one of those. And hence it can't be of the form greatest prime divisor bounded by 11. And so that's where this primitive divisor theorem comes in and can be helpful. So this is a relatively new result. And again, the proof is a real sort of tour de force. It requires pretty heavy machinery from linear forms and complex and p-adic logarithms, and then very, very substantial computation. But it's not sort of mindless computation. It requires a great deal of cunning. It was computation that people felt, oh, you couldn't do this. It's far too hard. It's solving 2A equations to sort of degree 1,000, which generically you can't do. But for these particular cases, we've got some extra structure that helps. So that's a sort of relatively recent sort of tool we use. And a much older tool is to go back and understand that the term they use is a fairly old-fashioned one called rank of apparition. So if a prime is going to show up as a divisor of a term in a given Lucas sequence, or a given recurrent sequence in general, then we call the rank of apparition the smallest index for which that prime shows up. And this goes back to Carmichael. So it's more than 100 years old, this result, was that for Lucas sequences, either the prime L never shows up, it never divides any terms, or it divides the Lth term, or it divides the L plus first term, or it divides the L minus first term. Okay, so that's kind of neat. So it shows up no later than the L plus first term. So how this works, if you put this all together, is that if we want to find, for instance, all the elements of some given recurrent sequence whose prime divisors are bounded by 11, you only have to go up to the first 12 elements and check. And then beyond that, everything's got a primitive divisor. So it's not 1 of 2, 3, 5, 7, or 11, and you're done. And so that means that basically reduces this to, on some level, a finite problem. Okay. So in our case, as I mentioned, the sequence we're going to look at, we're going to fix a prime p, and we're going to look at the sequence of powers of tau of powers of p. So one sort of trivial thing, tau of p squared, et cetera, et cetera. And we are going to associate this to a Lucas pair and a corresponding Lucas sequence. Now, in fairness, again, generically, this is a Lucas sequence. It just sometimes isn't, and I'll say why. So our starting point, again, we have this identity, which it was proved by Mordell, that this recursion that basically says you get tau of p to the m. So you get the, I guess I've indexed it here, the m plus first element in the sequence you get from the previous two with these coefficients. So Fibonacci, you'd have coefficients of 1 and 1. Here we've got coefficients of tau of p and minus p to the 11, but the principle's the same. So it's a binary recurrence sequence. And just to mention, so I'll go back to this, my apologies, that this is a binary recurrence sequence no matter what. It just fails to be a Lucas sequence sometimes. So if tau of p is actually 0, then the recursion says, well, so is tau of p cubed, tau of p to the 5th, et cetera, et cetera. And in fact, as I mentioned before, tau of p to the n, when n is even, is just plus or minus p to the 11n over 2. And so this thing sort of, it's still a recurrence sequence. It's just a kind of trivial one. It doesn't correspond to a Lucas sequence because Lucas sequences, you'd need these things to be coprime. So that's a situation that doesn't work, but that's a situation we just have to exclude. Our machinery doesn't tell us much. And moreover, we know the truth. We know everything that happens here. We know exactly what tau of p to the n does. So if Lamer's conjecture is false, this happens, nothing we can do about it. Okay, so if Lamer's conjecture is not false, then we notice that, well, powers of p could still divide tau of p, but the power that could divide tau of p is bounded by p to the 5th. That's because tau of p is bounded by twice p to the 5.5. And so you can just check that means that it can't be as big as p to the 6th. So if we actually suppose it's divisible by p to the r exactly, then what we do is we just divide that out. And it turns out that the bits that are left over do give you a Lucas sequence. So here things really do end up coprime, you get a Lucas sequence. So just like this. And just as a comment on this, p can divide tau of p. And this is another of these log-loggy kind of things that the conjecture is it happens infinitely often. So I think in the case of p equals 2 and 3, maybe even p squared divides tau of p. That conjecturally, so we know that p can divide tau of p, that's r equals 1. There's also r equals 2, 3, 4, 5. We would expect that 2, 3, 4, 5 occur finitely often, perhaps never again. But for r equals 1, we actually expect that to occur infinitely often. It's uncommon, and I think Kumar had a nice paper showing that the situations when tau of n and n share a common factor happens for 0%, for almost no values of n. Okay, so this can happen, and genuinely these you have to divide this out to actually get a Lucas sequence. But so how do we progress? So from this point on, I just want to notice we have, using this recursion formula, we have some nice explicit formula for tau of p squared, tau of p cubed, tau of p to the 4th, etc. And in these three cases, I really should have tau of p to the 5th on here. I think it didn't fit on the slide. In these cases, so tau of p squared, you can write as, it's actually this particular, it may be not obvious to see it here, it's a linear form in tau squared of p and p to the 11. Tau of p cubed is tau of p times a linear form in tau squared of p and p to the 11. And tau of p to the 4th is a quadratic form in tau squared of p and p to the 11. Okay. But in any case, what the observation to make here is that if we bound the greatest prime divisor of tau of p to the m for one of these, m 2, 3, 4, and the same will hold for 5, then what we have is that we've got a square minus a constant times p to the 11, square minus constant times p to the 11, square minus constant times, well, it's an 11th power. So square minus a constant times 11th power. We've got that this has bounded greatest prime divisor as well. So in each case, we get for some x and y, and now the y's here are in the first couple of cases like tau of p, and the x's are p, but in the last case, they're a little bit different. But in each case, we get that tau of p to the m, if we're assuming that tau of p to the m has its prime divisors fixed, then the same is true Do I mean this the other way around? I think I mean this inequality the other way around. Then the point is that the greatest prime divisors of y squared minus dx 11 are also bounded. So this inequality is backwards. And it's really for d is 1 of 1, 2, or 5. Okay. And so in other words, if I fix the prime divisors of tau of p to the m, then what I fixed, if you like, is we have an s, where s is that set of primes, an s integral point on a hyperelliptic curve. So fixed. So d is 1, 2, or 5. So this is a fixed genus. Let's see if I can get this right. 5. Fixed. It's a genus 5 hyperelliptic curve, and we have a fixed s integral point on it. Okay. And in general, what you can do then is apply the machinery, and it'll give you a bound. So the machinery of linear forms I wrote Q-adic here just to emphasize that Q is not P, the same P, but you're going to apply linear forms in both Archimedean and non-Archimedean logarithms. The best state of the art in this is by Bugeaud and Jury for this particular result. And we apply that to this hyperelliptic curve here. And we're able to get bounds on those. And when you combine those with the fact that we're assuming that x is p or p squared, that actually gives you a bound upon of this nature. So this is how you end up getting, for the small values of m, how you end up getting a lower bound upon the greatest prime divisor of tau of p to the m. Okay. And the positive constant is something one could work out, but it's small. Okay. And so more generally, if you go up this tau of p to the m, you use this recursion. It's sort of easy to prove by induction that in fact what you get, well, it's always divisible by tau of p if m is odd. And then the remaining bit is a degree m over 2 binary form in p to the 11 and tau squared of p. So we had for degree 4, it was a quadratic form. For degree 6, it's a cubic form. And in fact, it's this cubic form right here. I got it at the bottom. So in general, it's degree m form. And you know a lot about this. In fact, you can actually write down kind of explicitly what the form is. So it's basically a cyclotomic form, and that's going to be helpful. That's helpful for us for computations later, because basically these are about as nice as things get. Like if you want to compute the regulators here, fundamental units, this is the easiest stuff can get, essentially. So we have these forms, and in fact, it's even easier than that. They're SL2Z equivalent to these even simpler forms, if you like. So it's a very nice little sort of cyclotomic beast. And the idea is that what we can do, if we want to be a little formal about this, is that we take our tau of PDM. That's something where we're assuming that the prime divisors are bounded. And we factor it out. It's basically up to some fixed power of p. Again, usually r is 0 here. It's basically the m plus first term in our Lucas sequence. And what we do is we take the largest prime power divisor of m plus 1, and we do this factorization, which we can do because these are all what are called divisibility sequences. And the second last term here is actually an irreducible binary form of degree at least 3. At least it is after you have to eliminate some other small cases of m, but those are not hard to do. So what we end up getting is then if we fix the prime divisors of tau of p to the m, we end up fixing the prime divisors of this new big f of x. And so this thing's irreducible, it's easy to work with, and this gives us what's called a two-way-Mahler equation. Okay, so we have this. I think my inequality in the right direction here. And I'm going to hide the details, but the details include the fact that it's not just any old two-way Mahler equation. So you can't apply bounds off the shelf for this because we do understand the regulator much better. The fact that this thing is Galois helps an enormous amount. So instead of having to, you save some factorials in these things. And so when you put this all together, this ends up giving you that when you put it all together and use the fact that our big X and big Y actually are P's, you end up with a result of this shape. And here we're using the primitive divisor theorem to say that M itself has to be bounded by the greatest prime divisor of tau of P to the M. So that's essentially what the primitive divisor theorem tells you. You put all the machinery together and you almost get a lower bound of shape log log. And again, the way this machinery works, the truth is probably more like log. with some fudge factor. But the best we can do is log. Again, this is the kind of place where ABC can come in and give you a result that's one logarithm better. And so here you get log over log, which is bad, but doesn't look that terrible, except the problem is now you have to actually, we're going to choose p to the n to be the largest prime power divisor. And that the best we can do, I mean, it really could be this way, that gets us that extra logarithm as claimed. We get log, over log. So truly atrocious, but at least it goes to infinity. Okay. So let me just, I'm going to move into the more explicit stuff. So let me show you the general approach for dealing with say this. We want to understand this. And again, here it's tau of p to the m. We're going to use multiplicativity, but m is at least 2. And again, you can always, for small values of p and m, you can just compute this thing and see, hey, does this happen? So in particular, if you compute this, you'll find that tau of 8 really does have this form. Tau of 8 has 2s and what are they, 3s and 7s and 11s or something like that. Okay. And so the point here, we have to bring in all the machinery we can find. In particular, we have Ramanujan congruences modulo a number of primes, and this really helps, modulo 2, 3, 5, 7, 23. We don't need the 691 here, as far as I can tell. I haven't seen how helpful it is. So we do this, and this actually reduces possibility for the exponents. Then the primitive divisor theorem says that m is going to be bounded, I think I mentioned this before, m is going to be bounded by something like 12. Or maybe it's 11, or maybe it's 10, something pretty small for this to have any potential solutions. And then for the m that are at least 6, you get 2A Mahler equations and we solve them. And this is, a combination of linear forms and logs and lattice basis reduction. For these, it turns out not to be too bad. And this is something that Adela and Samir have been working very hard on, producing sort of general machinery for explicitly solving 2A Mahler equations and other S-unit equations. And then it's the small cases that turn out to be all the work, or most of the work. And that's m less than or equal to 5. So in particular, if we suppose this, then the Ramanujan congruences actually say that, well, of course, we said if p isn't 2, then tau of p squared we said is odd. So there's no alpha, so alpha is 0. But in fact, it can't be divisible by 5 or 7. And if it's divisible by 3, it's not divisible by 9. And so that means we basically have a much simpler equation. The right-hand side is really plus or minus 3 to the 0 or 1 times the power of 11. And what we do is we write down a couple of Frey curves. We treat this thing. So remember, tau of p squared is tau squared of p minus p to the 11. And so what we do is we pretend this right-hand side here is a constant times 1 to the 11. And we write down a corresponding Frey curve for this. And it's one of these two. You could just use one of them, but it wouldn't have quite the right level after playing around. So we use this one will give us a minimal model. And so we run through the sort of standard theorem of machinery. We have a particular Frey curve. And what we end up having is that mod 11, this thing's going to match up to some particular sort of cuspidal newform of given a level, weight 2. And the level is going to be 32. That's what's happening at 2. We understand that well. And then it's either 3 to the 0 or 3 to the 1, and it's either 11 to the 0 or 11 to the 1. And so we have to check these things. And this, again, at worst, is something of level basically 1,000. So it's not such a big thing computationally to deal with. And what we have is that the Fourier coefficients of our cuspidal newform should match up with the Fourier coefficients of our Frey curve, modulo 11. So we have something like this. Okay. And what we're going to do then is, so we have this equation, which gives us local information at various primes. And remember, we also have nice information mod 23, which is very helpful when you're looking at 11th powers. So what we do is we sieve. So we have this congruence here that the norms are divisible by 11. We have this congruence for every single L. That's a prime of good reduction for our Frey curve. So in particular, we avoid L is 2, 3, and 11, and we just sieve using primes that are up to 200. And if we do this sieve, it doesn't actually eliminate all possibilities, but it narrows it down to 2. So essentially 2. So one possibility narrows it down to is that you really do have tau squared p minus p to the 11 is plus or minus 3. And the other one is that tau squared p minus p to the 11 is plus or minus 11 to a power that's divisible by 11. So the exponent is divisible by 11. Okay. And the first of those cases, if you just use sort of basic algebraic number theory, you factor it the same way you might try to solve y squared plus 5 equals x cubed or something. You just go and factor in an obvious number field, you connect terms, and you end up reducing it to this 2A equation, which is admittedly fairly unpleasant. It's degree 11, not that bad to work with, but the basic machinery for linear first and complex logarithms and lattice-based reduction is suitably advanced that this is a sort of relatively routine computation. It will take a couple of seconds to show that the only solution is with u equals 1 and v equals 0. And that corresponds, if you trace it back through stuff I didn't show you, to p equals 1, which is a contradiction. So that's the first case. And the second case, you just rewrite it as this, and you basically have 2 11th powers, a sum of 2 11th powers being a square. And this is a beautiful sort of result of Darman and Morel, who proved in general that the equation x to the n plus y to the n equals z squared has only trivial solutions. And by trivial solutions, I mean solutions with absolute value at most 1. And so in particular here, it says that the only solution to this is with p equals 1, and that's another contradiction. So that's it. I'm hiding under the carpet the nasty parts of this computation because there is a fair amount of work involved to eliminate this. And if you extended it by pushing another prime in, then that prime is going to show up potentially in the level as well. So you're now going up to level about 14,000, and there's going to be a lot of modular forms, and it's possible that these things won't eliminate them. I think they will, but adding in the 17 means you're going up to a level beyond which we can sensibly compute a basis for the space of sort of cuspidal newforms. Okay, and so just to finish up, I just want to mention what do you do. So the tough cases are tau of p squared and tau of p to the 4th. And tau of p to the 4th is something pretty similar. You write down a somewhat more complicated Frey curve. Again, it's to treat this thing as if it was an equation with coefficients. It's something times something to the 11th plus another coefficient times y to the 11th equals another coefficient times z squared. You treat it that way, and that there's sort of naturally occurring Frey curve that corresponds to that. You write this thing down. You play the same kind of game here. Here, the difficulties are you've got issues at the prime 5 as well, because 5 ends up dividing the discriminant here. So that's one you can't use to eliminate other things, and it also makes the level higher. So complications there, but it still works out pretty straightforwardly. So that's what we proved. I think I'll stop now and take any questions.
Thank you, Michael. Let's thank Michael, the usual internet way of clapping that you can't hear. Are there any comments or questions or remarks for Michael? You can either, I see, maybe, I don't know how will I see you. You can either raise your hand in the list of participants, or you can say something in the chat.
Where there's few enough people, they can just unmute and fire away.
Yeah, that's true. That's true. So maybe while people are thinking about what they want to say, I can ask a brief question.
Oh, sure.
So let's go back to here. By the way, very beautiful talk, very clearly enunciated, and I also do understand you're hiding a lot of the difficult part, because I'm sure that space of modular forms that you have to search and then do the computations for it must be a little bit. What's the dimension of that space?
It's maybe 100 or 200, something like that.
Okay, so that's
so it's
the kind of thing.
But it goes up if you want to say throw in 13, 17, it goes up to 50, 60,000. Okay. So you're dealing with these matrices that are just completely crazy, right?
Yeah. But if we look at the heuristics, what we sort of expect, you sort of made a comment right at the beginning that you're getting triple logs for the largest prime divisor, and maybe you would expect a double log, but why wouldn't you expect the power of log? If you're thinking of these numbers as if added is true, they're growing polynomially. why might you not expect that the largest prime divisor will grow like like the logarithm or a part of the logarithm?
Well, I mean, I think you would sort of expect that for tau of p to the m. But then, when you put together tau of n,
yeah,
you can drop down a full logarithm. You really can, right? By just taking, right? You take a whole bunch of p to the n, which their large prime divisors are around the same size, and you end up getting the kind of the min, right? Or the max, pardon me. So by just taking a whole bunch of those, taking the product of those, then your n has grown exponentially, whereas the largest prime divisor hasn't. So you really do get like log that way.
So you think that's the right order?
I think for tau of n, it probably is. For tau of p, I think it probably is like log. It probably is like log p with some fudge factor. Log p to the 1 plus little o of 1. And I'm too confused to even tell you whether the little o of 1 should be a negative or positive exponent there. Right? It's something like that. I think isn't that right? I mean, I think because you can use multiplicativity to sort of lose a logarithm, right? Going from p to the n to tau of n.
Yeah. So one knows on average that tau of n has a lot of prime divisors, like more than usual.
Yeah. Oh, so more than usual, because I thought you proved as sort of more of an Erdős-Katz kind of thing, where it really was like log.
For tau of p,
for tau of p.
like but for tau of n, it behaves like log n whole squared.
Right.
So it's got more prime divisors. So it is an Erdős-Katz, but the mean is 1/2 log n squared.
Right. Okay. Yeah, it's an interesting thing to see what should the truth be in all these things. There's again lots of little results by people like Gareev and Sparlinski and people like that to prove these things, where they prove that the greatest prime divisor of tau of n is, I think they prove is like infinitely often bigger than log of n to the something like 33 over 31.
Oh, good.
So they show something like that. They said that sometimes like it really does grow pretty quickly, but it's one of these ones that they're almost all the statements are for infinitely often, or assume ABC, or assume.
Right.
I mean, you kind of have to, because it's just so hard to get your hands on tau of p on its own.
Right. It's disappointing how little extra you get from ABC though, for assuming such a powerful conjecture.
Yeah, exactly. I mean, maybe does even ABC with a number of fields even help? Or maybe a little bit. I don't know.
Not sure. Yeah. Good. Okay. Are there any other comments or questions for Michael?
I have a question.
Yeah, Ralph, go ahead.
Do you have any feeling for the number of prime divisors of tau of p? For example, could it happen infinitely often that tau of p is twice a prime? I mean, not a reasonable thing to believe. And more generally, I mean, it'd be interesting to understand the number of prime divisors of tau of p when p is a prime.
Well, I mean, I think your result, Kumar, does sort of an average, does show it. So you have an Erdős-Katz kind of thing on average, right? That it behaves the way you'd like it to. But I think to show like tau of p being 2p or even p times q, I think that would be really hard.
But that should be rare. So, right? So I mean, average you expect it should have like log p prime divisors. But I don't know. Maybe you can show you can't. I mean, showing that it never happens might be hard, but showing that it happens rarely, that it's a prime or has few prime divisors, is probably might be doable.
Right. I mean, I sort of wonder even, is it more likely to be tau of 2 times p than tau of p? I mean, is it more likely to be a prime, twice a prime than a prime? Right, because restricting it to be a prime means that you're restricting the thing has to be the form n squared. So it's, the argument has to be n squared. So maybe it's more likely to be twice a prime, but I don't know. I haven't really done this computation. It's the sort of thing that you go a very long way and it seems to be behaving a particular way, and then you get these strange sporadic things. It's a bit like p dividing tau of p, right? You check a few, it happens at 2411, and it doesn't happen again until you're up to 10 billion or something, and then it just happens again. So it's just one of these things that's a bit like Wieferich stuff, that it just seems to be, Is it 1 mod p squared? Well, no reason it couldn't be. So it just happens, you think, a piece at a time.
Right.
Uh,
Right. So Ralph, if your need is to know that it happens rarely, that can probably be proved. In fact, can be proved. But if your need is to know that it never happens, that's hard. That's probably impossible. Probably.
those are probably all in the same level as Lamer's conjecture. Of course, it doesn't happen, but we can't prove it.
It must be reasonable that it happens infinitely often, though, perhaps twice a time. Is that reasonable?
You know, it's one of these things I'd have to compute a little bit to see to see if I believed it. You know, if it happens infinitely often, it probably should happen at some point we can compute to, even if it's growing, because it's not going to be slower than log. I don't think. It's either going to not happen or it's going to be a log thing, and then it should show up if you compute the first billion n. But I haven't done that, so.
Okay, thanks.
It's actually quite interesting question to how you compute this, right? There's been quite a few good papers on giving faster algorithms for computing this, tau of n. It's really not trivial at all. The fastest ways to do this are quite sophisticated.